today look at the constant volume fixed mass reactor. We looked at the constant pressure fixed mass reactor earlier. We will follow pretty much the same approach except that we now notice the volume is going to be fixed and instead the pressure is going to vary, and correspondingly the analysis is going to change a little bit, and we will have to see how that changes. I am going to go through this a little bit faster when compared to what we did earlier, so that we just look at the modifications that we have done that we will do now. So the first law of thermodynamics applied here would be to start with, we have the same equation, but right away we can now say this is equal to 0 because you do not have any PdV work, PV work, okay, and nothing else, okay. So we just say there is no work done by the system, we just have only a heat interaction, and obviously then any change in the internal energy of the system directly comes from the heat or vice versa, okay, or the heat that is released goes to changing the internal energy directly. So here you now have du over dt equal to q dot divided by m. So all heat goes to changing the internal energy because it is constant volume. And then we have a similar situation like what we had before, that is we will now say we have a U, this is a total specific internal energy, this is now capital U divided by m, this is now total internal energy, right. Previously we had a small h is equal to capital H divided by m. Here instead of that we are now looking at internal energy. So this is sigma I equals 1 to n Ni capital Ui divided by m. Now capital Ui is molar specific internal energy of species I. Ni of course continues to be the number of moles of species I. So if you are now looking for du over dt, right, so du over dt now changes because of two things. One is the number of moles that changes with respect to time, as well as the internal energy of species I that changes with respect to time. So this is 1 over m sigma I capital Ui dni over dt plus sigma over all I ni d capital Ui over dt. There are two contributions. Here again we notice that the molar specific internal energy is a function of temperature alone. So for perfect gases, therefore dui over dt is equal to, at constant volume here, dt over dt. Now this is equal to capital Cvi dt over dt. So this is molar specific heat of species I at constant volume. Now we can now plug dui over dt as Cvi dt, but then what about dni over dt? We can do the same thing as what we did before. Again 1 over v dni over dt equal to omega I. So this implies dni over dt is equal to v times omega I. Therefore plugging all these back in the first law, that means we say we recognize that du over dt is q dot by m, we recognize that dui over dt is equal to Cvi dt, and we recognize dni over dt is equal to v omega I. We plug all these three back in the original equation and you can now get q dot divided by m equal to 1 over m sigma I capital ui omega I times v plus sigma I ni capital Cvi d capital T over d small t. Notice here again as before that v does not have an index I, so that's common for all the species, and similarly dt over dt is independent of species, they can be pulled out of their respective summations. So and then m gets cancelled for non-zero m, for those of you who are very picky about these. So we get q equal to v times sigma capital ui omega I plus dt over dt sigma over I ni capital Cvi. So from here we can rearrange to get, finally I am going to skip a couple of steps which are just algebraic and get this as q dot over v minus sigma over I capital ui omega I divided by sigma over I Ci capital Cvi, which I want you to understand is now a function of Ci and T. Okay, why? Because omega I depends on Ci and temperature, and you also have an explicit presence of Ci showing up here. Therefore this is a function of the concentrations and temperature. Of course you can we typically do not deal with specific molar internal energies, we typically deal with specific molar enthalpies. So you look at these tables like Janov tables and so on, it typically lists enthalpies rather than internal energies. So you could now convert that. So for ideal gases ui equal to hi minus Ru T, and Cvi equals Cpi minus Ru. Okay, so dt over dt is equal to q dot over v plus Ru T sigma I omega I minus sigma over I hi omega I divided by sigma I Ci capital Cpi minus Ru. The reason why we are actually having a universal gas constant show up here is because we are dealing with things on a molar basis. Okay, so you would have a specific gas constant only if you are using things on a mass basis. Therefore this is appropriate. I would like to make a few comments. We will in the future look at these kinds of expressions or terms but I want you not to get confused at that time. Sigma I omega I is non-zero primarily because the number of moles in a chemical reaction is not necessarily conserved. It's the mass that gets conserved. So if we were to actually look at omega I as the amount of mass that is produced per unit volume per unit time, okay, for which we will assign a symbol Wi later on, okay, then sigma over all I of Wi will be equal to 0, because you don't have any net mass that is produced or consumed if you now try to sum over all the chemical reactions, chemical species that are produced and consumed on their mass basis, okay, but that is not true when you are now trying to have omega. Okay, keep this in mind, because later on we will be looking for a sigma Wi and plug it as 0. You should not get confused. Okay, the English alphabet gives you 0, the Roman does not give you 0. So if you want to quickly remember that way, that is also fine. Roman is molar, English is mass. This you can now write Hi as Hf naught I, okay, plus sensible enthalpy. Okay, the Hf naught I times omega I, that combination sigma I Hf naught I omega I will be the net heat release rate in the chemical reaction. Okay, so it is finally coming from the standard heat of formation times the rate at which it is formed for every species added all together is the total heat that is released in the chemical reaction. Okay, so and then you will have a sensible enthalpy part that will stay. So these things will show up as we go along more explicitly. We will just don't worry about it now. So this, as before, is a function of Ci comma T. Keep that in mind. Now here, since the volume is constant, one over V dNi over dt is equal to omega I can be directly written as dCi over dt is equal to omega I. Previously we could not do this. Okay, previously we had to notice that Ni divided by V is equal to Ci, and V will change with time. So we had two terms for contributing to the rate of change of concentration. Okay, one because of the chemical reactions, the other because the pressure was constant, the volume was changing, and since the volume was changing, the concentration was changing. But since the volume here is constant, we don't have to worry about that effect. Okay, so the concentration change is only due to the chemical reactions here. Okay, or in other words, you could take the V directly within the derivative without any effect and get the concentration right there, and that is what we are looking for. We are looking for a time derivative of concentration as a ODE. So this is again a function of Ci and T. This is because of the chemical kinetic equations that we saw earlier on. So this is like a fairly large expression for each of those, and n equations there. Okay, and this is like typically what you would get solved with a package like Chemkin. Okay, so where you advance in time and see what happens. But now what we that is with a constant temperature. But now what we are saying is we will now have this affect the temperature. Okay, and then the temperature will change. That's essentially the idea that we are talking about. And so here dP over dt is of interest as a derived quantity. That means we now have these two as a closed set of equations. We have n plus 1 equations and n plus 1 unknowns, where n unknowns are Ci and n equations are these. Okay, so this is you should say really this is I equals 1 to n, and T is the n plus 1th unknown, and this first equation here is the equation corresponding to that, but they are all coupled, all of them are coupled. So once you do this, you should be able to find out dP over dt, which is of interest here. So the way we do this is to go back and say PV is equal to sigma over I Ni or ut. So V dp over dt is equal to or ut d by dt of sigma Ni plus or u sigma Ni dt over dt. That means there is a contribution because of change in the number of moles and a contribution in, because of change in temperature with respect to time towards rate of change of pressure. So this gives you dp over dt equal to RUT, take this V over here, right, and then get this derivative inside the summation, also the volume inside the summation. You will now have a sigma over I 1 over V dNi over dt, which is nothing but omega I. Okay, so this gives you a sigma over I omega I plus you can pull out the dt over dt from the summation, get this volume over here, and then that becomes the concentration. So you get RU dt over dt sigma Ci, right. So that's a function of Ci and T, which can be evaluated once you have solved for Ci and T. This is not coupled with the other. Okay, so you can get this. So this again formulates the constant pressure, constant volume fixed mass reactor. To solve this is not a joke. Okay, if your n is a fairly large number, shouldn't say fairly, no, I shouldn't even say fairly large, even if it is modestly large, it's going to be complicated. You got to pray to your gods that n is like 1. Okay, then you are in decent shape, but even then it's difficult, because this term here that's showing up here and here is going to be so huge. You're going to have the temperature sitting on top of a tree like an exponent to the E minus E over RT there. Okay, so that's very difficult to handle. There are numerical techniques for these. Okay, so you have to use like some stiff reaction solvers, so stiff equation solvers. So there are special numerical techniques that can handle these simultaneous equations. So let's now look at the other two ideas that we had on open flow systems. So the first of those is the well stirred reactor, which is typically abbreviated as WSR. It is also called as a perfectly stirred reactor many times. Okay, and of course that could be abbreviated as PSR, and that would kind of like rhyme with the next one, which is a plug flow reactor abbreviated as PFR. So you could think about PSR versus PFR and so on. If you don't hear me right, then you could get confused between the two. So we don't want to get into all that, so we'll just use WSR, okay, for the well stirred reactor. So or perfectly stirred reactor. I'll just use some space below PSR sometimes. Historically it is also referred to as Longwell reactor. Because of the person who came up with this. It turns out apparently that Zeldovich actually came up with this 10 years earlier in Russia. So whatever you can think of during the time that Zeldovich lived, he would have done it before other people did. That is Zeldovich for you. He is like a father figure in combustion. So here what we are talking about is right. So you have an inlet and you have an outlet, and so you have a m dot I in and a corresponding yi in and a h in, hi in, you can say hi in, there is mass specific enthalpy of species I at the inlet, and correspondingly we now say you have a m dot I out, yi out, hi out, and so on. But all these things, of course, you now have a control volume that is that you apply within this reactor, just pairing the inlet and the outlet, okay, and consider a q dot that would get out of this reactor with the following characteristics. So it has a fixed mass flow rate, so that means sigma mi in is equal to sigma mi out, equal to I am sorry, sigma mi dot in equal to sigma mi dot out equal to sigma equal to m dot, okay. So you have an m dot, we did not use m dot here, that is the reason why I was apologetic. This is a fixed mass system, okay, this is a fixed mass flow rate system. So when you say fixed mass flow rate, implicit in it is that we are looking at steady state, you do not have any accumulation of mass or depletion of mass, yeah. So and then of course you are now looking at the reactor having species, all species with concentrations whose spatial variation we will not worry about, okay. This is a steady state, that means we are not looking at any temporal variations as well, that means it is not supposed to vary right. So if it is not supposed to vary, well, that means that you don't have to look for differential equations of evolution of these with respect to either space or time, okay, but they will depend on parameters. What parameters? Typically we are looking at what is the size of the reactor that you want to work with, okay, and what is the heat out that you want to get out of this reactor. So depending upon these and the input conditions, you will get the corresponding output, or you will now get the composition inside the reactor and the temperature to attain based on what is the size at which you want to operate this reactor. Size is given by m dot, okay, that is like the throughput, and what is the heat that you want to get out of this. So these are now like the key parameters in the problem, yeah, okay. So then of course it has a certain temperature, pressure and volume, okay, and of course you could ultimately we will see this, there is a relationship between these. It is like you are handling a certain m dot at a certain pressure and volume, okay, that will relate to a certain density, alright, and with that density for these mass fractions you will now get the partial densities of each of those species to be fixed correspondingly and so on. So there are relationships that we will be working out among these, okay. So this has a an inlet and outlet of for steady stream of reactants and products respectively, that is reactants get into the inlet and products get out of the outlet. Now when do you get this kind of situation where you do not worry about these details, is when you now have high velocity jets of reactants coming in and then getting into like a tumble or a huge swirl or something of that sort, okay. So and then finally something comes out, so it is so chaotic inside that you do not want to worry about it, right. So experimental reactors employing high velocity jets okay. Offer this situation. Ideally, okay. The interesting thing, as we will see, is what we are interested in. Okay, we are now looking for algebraic equations without any derivatives, right, in concentrations and temperature. Again, those are the ones that we are interested in. So the concentrations obviously depend on the reaction rates, and the reaction rates depend on what are the reactions. So in principle you could actually use a reaction scheme of a large set of reactions, detailed elementary reaction steps involving whatever species that you are interested in keeping track of that are going to happen in this reactor and come out of there, right. And typically this is good for doing relatively quick, I say relatively because it's not quick to start with, okay. You still have like a huge set of nonlinear algebraic equations to solve, which is not easy, okay. But you are not bothered about the spatial distribution, the temporal evolution and all those things. You are not really worried about the geometry and all that stuff, right. So relatively quickly you can get things like pollutant formations, like for example you are interested in NOx, okay. So you can actually get a fairly good handle of what would be the NOx production from pushing in so much amount of air and so much amount of fuel into a reactor that is going to be operating at this particular pressure, this big a reactor and so on, okay. Or maybe carbon monoxide production. Why carbon monoxide production? Let us suppose that you are now trying to push a lot of fuel in there and maybe also corresponding amount of air, okay, for complete oxidation, but this volume is not big enough for complete oxidation to happen, and before complete oxidation can happen you now have products coming out. You are going to be primarily looking at incomplete combustion products, right. That means you are going to have some carbon monoxide, that is a pollutant, you see. So the volume available is going to also constrain how much reaction can happen, and therefore you can estimate pollutants based on that as well, okay. What we will also see is typically this is used to design reactor sizes like the volumes, okay, based on another idea of what is called as residence time, okay. So essentially what happens is you now have a reactor and you want to have a throughput of reactants coming in, reacting and producing products and that go out. You want to first of all decide how big this reactor should be, right. For this you have to have a notion of what is the residence time of these species inside this reactor by the time they could actually go through all the chemical reactions and come out as complete products. So for complete products we will now use the concept of residence time that will be related to the volume, okay. So that is another way of doing this. The third and very interesting idea with which you can actually use this is something like flame blowout, alright. And how does that work? So it is like, let us suppose that I have a reactor, okay, and then I am now trying to pump in more and more and more of the reactants in, and at steady state we are now expecting the same mass flow rate of products out, alright. And of course for a given volume you are now going to have incomplete combustion progressively, but at some stage it is simply not possible for you to combust at all, okay, as you now throw in more and more reactants at it. That makes sense, but how are you going to get this out of a model like this? The answer is you now have a set of nonlinear algebraic equations that you are looking for, which may not have a solution at all for certain values of m dot or q dot, okay. Let us suppose that you are trying to extract a lot of heat out of the system as well. You can quench, right. So for the set of parameters that you are employing, you may actually get into a no solution region, which now begins to correspond to a flame blowout situation. So yes.
If we say that yi is independent of time.
Yes, everything is independent of time here.
What reactions are occurring?
Reactions are occurring all the time. So whatever you are talking about, everything is happening all the time. That's like a dynamic process. Okay. As you speak, right, you have now reactants coming in, react and produce products or intermediates and products. Everything is happening. So you now we are not bothered about the spatial variation. Okay, so in reality, what might happen is, as you come in, you have more of reactants here, okay, more of intermediates here, and more of products there as they go out. But we are not worried about that distribution. So if you are not worried about that, all you have to say is you have in this reactor for a given set of reactant inputs, right, you are going to get, in fact the question that you are asking has to be approximated this way. We are looking for this output of products, okay, but we don't resolve the spatial, we don't spatially resolve between somewhere here and somewhere inside, okay. So in that sense it is like saying it's all perfectly mixed, all right, and you are now going to get out these species, okay. So it is, we will try to relate to what we did for the adiabatic flame temperature while we do this, okay, except we are now going to be able to parametrically vary things here. So we don't have a spatial variation, we don't have a temporal variation. The difference between the adiabatic flame temperature calculations and what we did earlier for the fixed mass systems, as well as what we will do later on for plug flow reactor, is we can track variations between the starting point and the ending point, which we didn't do earlier, okay. Here we are not doing that. So the question is, well, how is it different, okay. The answer is, as far as products are concerned, we are going to primarily get something like what we did before, and they are not exactly equilibrium products, but we will get from similar calculations as we will see, okay, but we will not do the spatial variation, right. So in that sense it's difficult for us to understand how it can be steady state, okay, but in reality this is what we are expecting to have. So okay, so no spatial variation. No, I meant to say, I meant to write out something that I got distracted from. Let's just write out NOx formation, incomplete combustion, incomplete combustion can be quantified from combustion efficiency, okay. So you can find out how much of the original fuel that you put in has been completely oxidized, okay. So and then that denotes what's called as combustion efficiency. So that can quantify incomplete combustion, and so you can get that kind of quantity here, incomplete combustion and flame blowout, okay. Flame blowout could be studied. So considering the complexity of the fluid mechanical process that's happening inside in reality, this is a quite powerful idea, okay. Just use only algebraic equations to do this. It's actually a fairly powerful idea here for these kinds of complicated situations. So now let's look at the other thing that we said, no spatial variation. No spatial variation of concentration or temperature considered. considered, and steady state assumption, okay, or steady state assumed, okay, no time variation, as well. Okay, so this should lead to algebraic equations, as we will see now. So global balance for individual species. The reason why I am calling it global mass balance is we are not applying it to any particular point in this reactor. It's applied to the entire control volume. When we want to derive a mass balance for each species, we will actually take a control volume approach and do like something like a global balance, but we will keep in mind, we will now make use of the fact that the control volume is arbitrarily shaped, and then we will be able to notice then that the equation that you derive there is actually valid at any point. But here it's not really valid at any point because you don't have any spatial distinction at all. Okay, so this is still certainly a global mass balance. So at steady state, for each species I, m dot I out equal to m dot I in plus omega I times V. I am sorry, made a mistake. We will now use Wi. Okay, so this is actually like a verbal equation. Okay, we just put in symbols here, but it's essentially like a intuitive idea. You think of your bank balance, for example. Okay, so this is what you had to start with, and then you put in some money, you get some more bank balance, right? So anything can be budgeted like this effectively, right? So whatever you get out is whatever you put in plus what you created. This now is actually for a particular species. If a species is a reactant and it's going to get consumed, this is going to be negative, so you're going to get less of it when compared to what went in. So so strictly speaking, we should say this is I equals 1 to n, and keep in mind this is a dot here, that means these are rates. So we are looking at something like kilograms per second. Okay, Wi then is the okay, net rate of production of mass of species I per unit volume. So long as we were dealing with fixed mass systems, we were always handling things on a molar basis. Okay, but the moment we are actually shifting to a open flow system, we start dealing with things on a mass basis. Okay, so here instead of using omega I as we did before, we use Wi. So we shift from Greek to English. Okay, and this is a mass basis. And this is what I was trying to point out. If you now get a sigma Wi, you should look for it to be 0 because mass is neither created or destroyed totally. Okay, but so long as you have a sigma omega I, that's all right, wherever. Okay, because number of moles is not necessarily considered. So look at what's going on. This is mass produced per rate of mass produced per unit volume. So this should be kgs per second meter cubed. So times the volume should get you kgs per second. Okay, so these are kgs per second mass flow rates. Okay, So we know that Wi equal to omega I times capital Wi, where capital Wi is the molecular weight, of species I. Okay. The distinction between my W's and omegas is you have this little curly thing for W's, whereas that is absent in the omega. So you have to look for that little thing there. Okay, and m dot I equal to m dot times yi, and this m dot is the total mass flow rate, which is a constant because we have steady state. Okay, and that's a parameter in the problem that tells you what's the throughput we want to handle in this system. Okay, so if you now want to put all these things here, we get omega I capital Wi V plus m dot yi out minus yi in, yi out minus yi in equal to 0, I equals 1 to n. Okay, now you could leave it as it is and then say this is given. Okay, this is a parameter. That means you can have a set of yi for any m dot. Okay, that means you can send in a particular composition of reactants at any level of mass flow rate. You can have a large mass flow rate of the same composition or a small mass flow rate of the same composition. Yi in for I equals 1 to n will refer to the composition that is sent in. M dot will actually refer to the size, how much you are trying to push in through this, right. So this is given, this is what you are trying to look for. Okay, now since we do not make a distinction between here, here, here and here, we do not have a spatial variation that is possible. Okay, what we are looking for is only mainly what is happening inside as like a whole quantity, right, and therefore you can say, because you have to bring in the volume and so on, you now say yi out is the same as whatever is the yi inside the control volume, because you just can't make the distinction, okay, spatially. So here we suppose, right, yi out is identically the same as yi CV, where yi CV stands for the composition in the control volume. Okay, and of course keep in mind this omega I is going to be a function of concentration of individual species and temperature. So temperature is coming into picture here and we do not know that, right. So for that we need to solve the global energy balance. So you get one more equation for that unknown, and that is what we should be pursuing. Okay, so global energy balance. Q dot is equal to I equals 1 to n m dot I out hi T out minus sigma I equals 1 to n m dot I in hi T in. Okay, So let's just go back and write YICV as simply YI. Let's not have any subscripts anymore for what we want to calculate. Anything that we want, we try to not have subscripts, superscripts, primes and all that stuff. That should be like the main quantity. So here what's happening is, this is the product enthalpy, enthalpy rate. I stand corrected. This is the rate at which enthalpy is coming out. Okay, this is the rate at which the enthalpy is going in. The reason why we have a rate is because we now have an m dot. The dot is what's making it a rate. Okay, and this is beginning to look like what we did earlier. Okay, so when we did the adiabatic flame temperature calculations, we were looking at energy, not the energy rate, right, not the power rather. So here you're looking at Q dot. Previously we said Q, and for adiabatic flame temperature calculations we set Q is equal to 0 and then equated the product enthalpy, not the enthalpy rate, equal to the reactant enthalpy. Okay, and then we tried to find out the T out, which is what we are going to do now as well. Alright, so it's an algebraic equation that we had earlier, which is also same thing as what we are doing here. You see, except the m dot I out was calculated based on equilibrium calculations earlier on, whereas here m dot I out is nothing but m dot times yi out, and yi is going to be now calculated with this equation taking into account the chemical kinetics. So this is a difference. So this is the real process, that was a hypothetical process, you see. So here so you want to now say this is a parameter, and this is what we want to try to find out, and we suppose T out is equivalent to identically equivalent to TCV, which is the temperature in the control volume, because we can't distinguish, and that would be equal to C. This is given. You might argue with me that wait a minute, we can't distinguish between here and here as well. Okay, don't ask that question. Okay, that's essentially the point. We are not really doing anything bad. Strictly speaking, this is out. That's okay. Okay, this balance is correct. We just drop the subscript. That's it. Okay, so Q dot is equal to, we can now pull m dot out, sigma I equals 1 to n yi hi of t minus sigma I equals 1 to n yi in hi of t in. So here yi in is also given, as we said earlier. That means we need to know the inlet composition, and recall hi of t is equal to hf naught I plus integral T ref to T small Cpi dt. Okay, so we are writing everything in small. It's small h here, small h here, small Cp. Okay, this is because this is on a mass basis. The capital Cp that we wrote earlier for the fixed mass reactors is on a molar basis. Okay, so we now have two equations and two unknowns. We will pursue this a little bit more tomorrow. This is a good time to stop, because we are now looking at the picture. Okay, we will now do some finishing touches tomorrow and then proceed with the plug flow reactor. Yeah. Thank you.